Uh, Hello everyone. My name is Reza Said Kendezi, and today we are going to talk about the time synchronization using the standard IEEE 1344. This standard basically codifies the way that time should be treated, and we have to note that the time is not just an auxiliary signal, but basically the time is the foundational infrastructure that makes sure all part of the systems, especially the complex systems, uh, speaks the same temporal language. But why does it matter? Because if we have a distributed system like smart grid or a 5G network, and if the subsystems in that distributed system doesn't agree on what time it is, basically the causality will collapse and basically the logins would not have any meaning. The control system would misfire and basically the general system would be destabilized. Now, IEEE 1344 basically is a formalized answer to that challenge. Okay. Uh, this standard uh, basically creates principles, real world implications, system architectures, the metrics for evaluating the time synchronization, and the application of this synchronization. Today we are going to discuss about those stuff and those topics, and we're going to learn how to make sure that our system is synchronized and all the clocks in our system is synchronized. Now, let's begin with the concept that is in the heart of that standard IEEE 1344. This standard base kind of like message is that the time is not just a background parameter, and we have to deal with it like a primary coordinate of our system state. Basically, every physical system and every physical measurement, it doesn't matter if it's a voltage or like pressure or a position, they exist in the context of when it was recorded. So if that when the time is not reliable, then it doesn't matter how accurate those measurements are, uh, we cannot trust them. There is four key domains that illustrates the foundational kind of like effect of time. Okay, the role that time plays in our system. The first one is distributed sensor networks. Okay, if we have a network, for example, spread over 500 square kilometers, and we have 100 sensors uh, that record data, but their clock is not synchronized. Okay, even if that synchronization is a very tiny number, like maybe 10 milliseconds. We cannot compute the accurate epicenter triangulations on that area. So the geospatial reconstruction basically breaks down. Or in the control system, uh, if the control loop, more specifically when we're dealing with a high speed application, like motors or drones or robotic arms, if they don't operate in a consistent time steps, okay, eventually we get to the point that the feedback arrives late to that time misalignment. So either system become underdamped or oscillatory or even unstable. Okay, or in a data login, uh, basically when we talk about logs, uh, they are our only source of when the failure is diagnosed, okay, when we're dealing with a high risk system, okay, like thinking about, like try to think about the aviation crashes or medical devices. If timestamps are wrong or even missing, okay, basically it's impossible to recreate what really happened. Okay, so the integrity of your evidence collapse. In digital communication like 5G, these networks depend on a precise slot timing. Okay, a little bit of drift in the base station clocks basically result in overlapping transmissions or dropped connections or even bandwidth collapse. Okay, so these are the why we say that the synchronization of the time and our clocks within the system is important. Now, what are the consequences of time alignment? Okay, uh, when these kind of stuff, that this time misalignment happens, and we lack a consistent notion of time, we can typically classify the problems into four failure mode. Either it's a control degradation or event a correlation error or sensor fusion artifact or security and forensic breakdown. Now, let's talk about each of them. Like the control degradation, when we want to like talk about it, let's consider a PID controller receiving feedback data that is misaligned like by 50 millisecond. Okay, that control system may respond to the old data, resulting in overcorrection or oscillation. So the system basically begin chase its tail. Okay, so this is what happened, the consequence of this misalignment in control degradation. Okay, or in when we talk about the event correlation errors, for example, in fault detection, logs from different devices must be temporarily aligned. So the time should be aligned. If one sensors, uh, for example, logs an overcurrent at a time and another logs a relay trip with a non-aligned time, these were these events related? Without synchronized time, the answer is basically ambiguous. So we cannot follow the causality of the event. So when the overcurrent happened, okay, and when the relay trip. Another aspect we said is the sensor fusion artifact or data fusion artifact, okay? When we talk about the autonomous vehicles or radar or GPS, the inertial measurement must all be time aligned. So we have a coherent situational awareness. A 10 millisecond error basically can cause object misplacement by several feet, okay, resulting in false positioning. Okay. Or when we talk about the security and forensic breakdown, like for example in financial system, if trades are not recorded with a synchronized time tag, okay, and the time tags are not having the proper accuracy, okay, basically if the clocks are off, you can prove when an order was placed or executed. So there would be chaos. And actually, we are going to see one example of that incidents happening in past, so in future slides. So it created chaos. There are penalties by regulator that could happen, and tons of other kind of like cost in our system. Now, let's talk about some of the examples, some of the disaster that happened because of these time errors, because of the desynchronization of those clocks and times. Now, the first example is the Northeast power system blackout in 2003, which basically affected 50 million people across northeastern US and part of Canada. Uh, it was caused only because of the phasor measurement unit synchronization because the GPS signal was lost. Okay, so when we talk about the PMU or phasor measurement unit, basically PMU require a microsecond level synchronization. So it could detect the phase angles of a voltage or current when we talk about the like a multiple grid nodes in power grid. Okay, if we don't have an accurate time, the phase angle errors would accumulate. The state estimators, which basically calculate the system stability, received false data or incorrect input because of that time drift. Okay, so operators received alarm too late. So all that would make a huge misleading in a protection system, which in that specific case resulted in a full instability of the system, and it was a full blackout in Northeast power grid in US. Another one is in 1996 when a launch failed, when a shuttle launch failed. Basically, what happened is that that rocket activate the self-destructure 37 seconds after the launch. That was $370 million project loss. Okay, what happened was that the software reuse in that project assumed different clock behavior. So the inertial reference platform had a data conversion error caused by that clock mismatch. Uh, Exception occurred simultaneously in both primary and backup system, and because of that, both were executing synchronously, but synchronously wrong because their clock was misaligned, mismatch. Okay. Another case is a flash crash in the stock market, the US stock market. Okay, which it caused a nearly $1 trillion problem in just 36 minutes. We had multiple exchanges that were operating on a desynchronized clock. So the uh, 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 execution logs, okay, showed a contradictory sequence. Like for example, the trade B appeared executed before trade A because of that desynchronized clock. So that was a misleading timestamps, which caused a huge problem in the financial market. Another example is medical infusion pump recalls when uh, that medical device administered kind of like administered an underdose over time because of the time drift. Okay, and it was a massive recall. What happened is that the internal real-time clocks differed by like a little bit bigger than 2 minutes per week. Okay, there was no synchronization network mechanism like the NTP or PTP protocols. So the medication scheduling basically become misaligned with the actual patient timing, the prescription that was set for that patient. So you see how time is important in a variety of fields, and how could time desynchronization create a very huge disaster. Now, now that we've seen what happens when we don't have a synchronization in time, let's talk about the central solution that IEEE 1344 basically proposed. This standard, which is a standard for a synchronization, measurement, and control system, is it does not define a specific protocol. You have to note that, but it defines a framework. Okay, and that framework is applied and can be applied to the diverse variety of the field and industry and system. The goal is to make sure a temporal integrity. Okay, so we have a synchronized time. We could trace the event. Okay, and we have a system-wide consistency. Let's break down the five important pillars that exist in this standard. One is that we have to make sure the time tagging is a standard. Okay, what that means. Uh, this standard defines how we have to label every critical event or measurement, or when we send a control signal. Okay, and the tag, how we tag that event should be precise and traceable timestamp. Okay, uh, that part includes format, resolution, and even reference and associated quality metadata of that time tagging. Okay, so these time tags allow us to correlate data from diverse sources. Okay, for example, a phaser measurement captures a measurement at a certain time, okay, with a known accuracy. Okay, if we tag that with a precise traceable timestamp, then that measurement would not be ambiguous, and we could verify it, and we could trace the data, the measurement, and the action that we get that we had based on that measurement through our log history. Now, this tagging basically enables forensic reconstruction or real-time control alignment and a multi-system data fusion. So we can basically connect several subsystems when we have a synchronized, accurate, precise time tagging into our events for our events. Now, next important kind of like concept is the hierarchy in synchronization model. Okay, what IEEE 1344 defines for this role is first of all, we have to have a primary reference clock. So this is the hierarchy. We have a primary reference clock. It could be a GPS or an atomic source. Sorry. We have a grandmaster clocks, which basically distribute the time to the local subnetworks. Okay, we have a boundary clocks that intermediate devices that pass time between domains. Okay, and we have an ordinary client, which is basically the end device that uses that time tag, like relays or PLCs, okay, or PMUs that we discussed. Now, this layered approach basically make us able to like have a fault isolation. We have a scalability and segment maintenance. So it shows how we structure power distribution or like IP routing. Okay. In this hierarchy, you have to note the time flows from top to bottom, from that most accurate one, that primary reference clock, all the way to the consumers, which is the ordinary client. Okay, so all the devices retain the metadata about the time source and the quality. Quality of the time source is also important. Okay, it's not just a synchronization. We have to know how reliable that source of timing is. And failover strategies must also be documented. So if something happened, like for example, if that GPS failed, okay, now what is the strategy and what we should do, and if that happens, what is the history recorded for that incident? Now, the third important aspect of this standard is the protocol agnostic implementation. So we do not enforce in the IEEE 1344. This standard does not enforce particular protocols. We don't need to specifically have a PTP or NTP. That's flexible. We can use whatever protocol that we want, so that we allows time to be distributed using GNSS or PTP precision time protocols or inner range instrumentation group that we call it IRIG class B. Uh, 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 excuse me. Or network time protocol, that NTP that we called. So this flexibility makes makes this standard suitable for legacy systems, okay, or modern Ethernet-based automation and mission critical control platforms. Okay, the focus is the interpretability. A system should always know where its time came from, how accurate it is, and whether that time source is still valid or not. Okay. The fourth aspect is system monitoring and alarm. This standard formalizes basically how time-related failure must be detected, and we have to act based on those detection. For example, if a boundary clock stops receiving GPS, so it should enter the holdover mode. We are gonna see what is the meaning of the holdover next in the upcoming slides. So it should enter when it lost the GPS data receiving. Okay, it should enter the holdover, notify the client, okay, of the degraded time quality, and log the event with a timestamp, okay, and the recovery point. So everything should be clear and recorded. Then alarm must trigger. Okay, these alarms can fit into any dashboard or like a SCADA system. Okay, so we know what's going to happen and we alarm that, okay, we lost the synchronization time. Now we cannot rely on the that top reference clock in our hierarchy. The fifth pillar is the traceability and auditability. So what do you mean? This is critical actually when we talk about the power system or aviation black box or financial compliances or medical devices. This standard IEEE 1344 mandates that logs must include is must. Okay, so is mandate. It must include all the logs, include not just the timestamp. It also have to have a quality class. So it's not just a timestamp. We should know how accurate that time is. Okay. Then we have to cryptographically sign where it's applicable, those timestamp. And it should be retained for duration defined by the sector. For example, all those records in a finance domain is normally recorded for 7 years. Okay, but what does traceability means? Traceability means that you should be able to use those timestamps to prove what happened, when it happened, how accurate that when or like the timestamp is, okay, and or was basically because it's history, and whether the timestamp was trustworthy or not. So where, what happened, when happened, how accurate that time estimation and time stamp is, and is it trustworthy or not? Now, there are several terminologies or important terminology that we have to pay attention when we talking about this standard and time synchronization. We use this terminology. We are gonna kind of like go over some of the important terminology because we wanted to like have a common ground. Okay, when we talk about time tag, we wanted to like have a common definition for that. So it's specific and there is no ambiguity when we talk about those. Now, let's just start with the key terms that we are going to use in IEEE 1344. The first one is time tag. Okay, the time tag is basically is a structured timestamp, okay, that labels when a measurement or event or control action would happen. Okay, it can include a resolution, like for example, nanosecond. It can include the offset and time quality metadata. Okay, so this is time tag. This is the definition of the time tag. When we say time tag, this is the what we're talking about. We have reference clock as a terminology, which is the root authority for the time. It normally is it typically like is a GPS or a rubidium source or cesium atomic clock. So it's the main reference that tell us the exact precise time, and we have to synchronize everything with that clock. So it's the center of our synchronization. We have time server as a term that is basically a node that distributes its time to the downstream clients. It could work with an NTP protocol or PTP. We don't enforce any protocols. So time server basically distribute the time from that main reference to all the clients, all the downstream hierarchy that we talk about. The offset is basically the difference between the client's current clock value, okay, and the reference time. Okay, it could be nanosecond, it could be microsecond. So we have the reference time, okay, but the internal clock of the client, and even when the client receive the data from the reference clock, it because it's physical system, we will have a certain delay. Is not gonna be, we are gonna limit that delay as much as we can, but we cannot mitigate it completely. So we are gonna have a very tiny delay between the master clock, that kind of like GPS or like the atomic clock that we have as a reference clock. When that signal of the reference clock uh, will be sent to the client, that delay creates drifts, creates offset. Okay, this is one of the sources, and one of the other sources is that if there is an internal clock in the client, that also could create a offset, which is the difference between the actual client clock and the precise value of the reference time. Okay, the term drift that we are going to talk about is the rate at that we describe as a clock would diverge from the reference clock. Okay, so drift is a rate of divergence. Offset is constant. So if you have 1 nanosecond offset, doesn't matter how long it passes, it remains the same. But when you have a drift, it changes because it's the rate of the diverge. Okay, so we have an error, and through the time, it would be bigger and bigger. The jitter, we define it as a short-term fluctuation in timing consistency. So it's a short-term fluctuation. It's not a long-term. It's happened for a specific period of time, and it will be gone after that. It's a short time variability. Now, skew is also the instantaneous difference in between time between the two in a time between the two clocks. So you have two clocks. It's in the second level of hierarchy. When you have like a server nodes or clients, you have two clocks. There is an instantaneous difference between the times, so they are not fully synchronized. There is a small difference between them, so that's skew. Now, when we talk about the holdover, I want to add that for your information because we use that in previous slide. When we talk about the holdover, is basically an action that we take after we realize desynchronization. Okay, and the definition is a mode where a time client maintains internal time using its own oscillator. When it's happened, when external synchronization is lost. So if we lost the synchronization with that reference clock, that top of the hierarchy, then the client should go to the holdover, meaning that it has to use their internal clock. But we have to note also, we already said that we have to alarm that, okay, we lost the synchronization to the system. So this is our internal clock. It might not have the right accuracy. Okay, so this is the alarm. Now, there are some system level terminology. Okay, that's basically is for several architectural models that we have to support different type of synchronization. Okay, that we have to discuss. The first one is the master slave or master client model. In this topology, we have one clock as a reference, like the GPS, and all the downstream will synchronize it themselves to that one clock. Okay, it's very simple, it's easily traceable, and it has a very clear hierarchy. But there is a downside to that too. So if we lose that uh, master clock, then all the system goes to the holdover. Okay, so that's very sensitive. There's a very high sensitivity. The quality of the signal that comes from master to all those clients. Now, another model is the peer-to-peer. In peer-to-peer synchronization, all the nodes in our system participate in a mutual time alignment. Okay, so there is no single master. Okay, we are going to have a very high resilience. Okay, but the downside is it would have a very complex algorithm. Okay, and if the nodes become hugely disagree with each other, okay, then we have an instability in our synchronization. There is a multicast model when a source like GPS broadcasts timing data over one-way channel, like satellite time distribution. Okay, these models are scalable, very efficient, okay, and has a low per client overhead. But they have a delay issue in and asymmetry issue. They have a they require a consistent calibration to make sure that the delay asymmetry is handled. Next model that we could employ the time synchronization is the hybrid model. This hybrid model basically is a combination of the master-slave model and peer-to-peer model. Okay, so normally like in a large power grid or aerospace platform, okay, we use this hybrid model. So we make sure that this has all the benefits, and because of the benefits of the master slave and peer-to-peer, we could kind of like get rid of some of the cons. Like if we have a master slave, then the instability of the peer-to-peer when the nodes are disagree, then it wouldn't happen. And if we lost in a master slave, if we lost the reference clock, then every client should go to the holdover. But in the hybrid system, the clients are also have a peer-to-peer communication. So if the master clock is off or have a low quality signal, then the peer-to-peer would kicks in and make sure that we could handle the synchronization. Now, Uh, the time distribution architectures in IEEE 1344, okay, uh, has a variety of architecture, okay. Uh, but why does the architecture matter? Because time, like a voltage or any kind of like signal bandwidth, degrades over distance or noise or any interference. So the design of your time distribution topology affects your system performance, the system reliability, the scalability of the time synchronization, and the fault tolerance. So it's not a one size fits. It's not like the one size fits all architecture. Instead, the IEEE 1344 enables a library of validated strategies. Okay, let's talk about a few of them. First one is the hierarchical. This architecture is like similar to the power distribution network or corporate IT network. A primary time source feeds as a grandmaster, which distributes time to the intermediate boundary clocks, which in turn synchronize the end device. Okay, so the layers are the layer zero is that traceable like reference. It could be atomic reference. Okay, the after that is a grandmaster with a holdover logic and fault alarms. Then we go to the next layer, which we have a switches and gateway with a boundary clock capabilities. And after boundary clocks, we have our clients and nodes, could be PLCs, could be sensors, could be servers, could be relays. The strength of this architecture is that it has a very high accuracy. The monitoring and control is centralized, and it's easily we could easily validate it and audit it. But It requires a redundancy planning, okay, to avoid single point of failure. Synchronization paths also asymmetrize and should be calibrated constantly. Now, another architecture is flat distributed. There is no master-slave relationship, so all clocks receive time directly from the reference. Okay, so the strength of these specific uh, uh, architecture, which basically multiple trusted time source broadcast directly to the client, okay, is that we don't have any central point of failure, and this architecture can adapt dynamically when the topology changes, when your network or your system changes. But it has its own challenge, like it requires a robust clock selection algorithm. Okay, and local clocks may drift independently without correction. So we have to note those challenges. Next architecture is cascade time distribution. It's a useful architecture in larger scale or geographically distributed infrastructures. Okay, the time is handed off across multiple zones, each with its own regional boundary clocks. Okay, so each tier in that architecture must monitor its own upstream time source. So there is a high accuracy time distributed on a backbone with aggregation devices acting as a regional boundary clock. So we have a still hierarchy, but we zoom that hierarchy. So we don't have one boundary clock. Every zone has its own boundary clock. So client must not accept time from multiple tiers. Obviously, we know if that happened, what are the problems that could be caused by this kind of like incidents. If there is a time quality degradation must be tracked. Those degradation must be tracked across handoff boundaries. So what we do in response to that is standard provides a mechanism. So it insert time quality metadata at each hop. It triggers alarms if cascade error exceeds any threshold. And it provides isolation zone for maintenance or failure handling. Now, next architecture is a redundant or voting architecture. This architecture has a multiple time sources that are available concurrently. Device, the clients use voting or arbitration or a fallback logic to select the best time, which one is the best source. Okay, it has multiple grandmasters for the clock, holdover oscillators with known gain profile is one of the other features of this architecture, and the time validators that flag all the problems and discrepancies are another feature of this uh, architecture. But we have to note that we are required to trust the hierarchy and validation threshold, Alarm generation on divergence between the sources is also required, and the sign logs to document failure events is also mandated for this architecture. Now, now that we discuss about the architectural models, we must know how focus on the actual devices and synchronization methods that basically is gonna be based on IEEE 1344. Uh, Without a stable, accurate, and verifiable source of time, the architecture is just a shell. Okay, so we have to kind of like pay attention to the primary time source, local oscillators, and synchronization interfaces. Okay, so uh, 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 what we mean by primary time sources. These primary time sources are devices that are ultimate authority for time in our system, and they are traceable. So it could be like a GNSS-based time sources, like GPS, okay, or Galileo. Uh, these sources, in these sources, accuracy is typically within like less than 100 nanosecond. And normally these sources are used as a grandmaster clocks. Okay. So, but when we talk about the GNSS based time sources, we have to have these consideration that susceptible that these sources are susceptible to spoofing and jamming. These sources require antenna placement and signal validation. So IEEE recommends multiple GNSS with real-time sanity check. Okay. For the primary time sources, we also have an atomic clock. It could be rubidium oscillators or cesium beam clocks or hydrogen masers. Okay. Uh, these clocks have an accuracy, as you could see, like the oscillators, the rubidium oscillator has the accuracy of around 10 to the power of minus 11, which is quite good accuracy, or the cesium atomic clocks has an accuracy of 10 to the power of minus 12. Okay, but each technology that we are talking about here basically has their own trade-off with accuracy and stability and cost and all the vulnerability that they could have. Now, beside the primary time source, we could have local reference option too. Okay. When we lost the synchronization, so we don't have access to that primary source, basically device enter the holdover mode. We already talked about that. Okay, so when we are there, then the local references kicks in. It could be oven control crystal oscillators, okay, or temperature compensated crystal oscillators. Okay, but what is important is that the maximum allowable holdover drift must be declared based on the IEEE 1344. Those devices must log when they enter a holdover, so we know when we are disconnected from the primary source of synchronization. And client must label the timestamps during that degraded mode. Now, another type of local is the synchronization interfaces. This type supports a wide variety of hardware and network interfaces. Okay, it could be like a one pulse per second clocks, or IRIG interfaces, or like IEEE 1588 PTP protocol or NTP protocol. Okay, the IEEE 1344 allows the combination of these methods. Okay, so provided the time quality metadata and alarm handling, okay, we should implement all of them correctly. Now, let's talk about some of the quality metric of different kind of like example of the protocols. Okay, uh, we have to monitor and have a logging time kind of like audit to see how the what is the performance of our clocks are and our architecture are. Okay, the metrics that defines this defines the threshold for these protocols, okay, are defined in IEEE 1345, and you can see that in the picture in the slide, and it defines basically how timing should behave. Okay, for example, accuracy is one of them. So we see that the PTP protocol has an accuracy of less than 100 nanosecond, when NTP is around 1 millisecond, but SNTP is around 10 milliseconds. So you can decide which one would answer your precise desired accuracy. So we have to use that, and this is kind of like required for each protocol. Now we have to have a hardware support. In PTP is required for best accuracy. NTP is optional to have a hardware support, but SNTP doesn't need that. We use PTP normally in power and telecommunication. NTP is normally used in IT networks, and SNTP is normally used in an embedded system. On the other hand, the PTP has a high complexity compared to the NTP, which is a medium, and SNTP is a low complexity. PTP has a high jitter or delay when sensitivity, when NTP and SNTP are much lower on that than that prompt. Now let's understand what this means. Let's go deeper into that table. Okay, let's talk about the PTP first, the precision time protocols. Okay, this protocol is designed for high precision environments like smart grids or aerospace or telecommunication. Okay, and the working principle is that the master clock sends sync packets to the slaves, to the clients. Now, all the clients measure the network delay using the timestamp message. Okay, and it requires a hardware timestamping. Okay, for a nanosecond level accuracy. Okay, the best performance for PTP is achieved when we have a PTP aware switches. So we have boundary clocks and transparent clocks. PTP is a default synchronization layer in wide area measurement system, and it ensures the synchronophaser stay within plus minus 1 microsecond. Now, on the other hand, NTP, the network time protocol, is designed for internet scale system like servers or enterprise network or web infrastructure. It has an accuracy, as we said, about 1 to 10 millisecond in ideal condition, actually. And it uses the statistical filtering, delay compensation, and jitter smoothing. And what and the communication that is used that this protocol uses is UDP or IP normally. This protocol is not ideal for high precision control, but is excellent for distributed logs. Okay. SNTP is a simple network time protocol. It's designed for lightweighted embedded system, printers, consumer electronics, you know, clocks, normal clocks, not the clock that we talk about in synchronization. There is no clock discipline in the SNTP, no statistical filtering, just time synchronization. That's why it has an accuracy of roughly 10 milliseconds, which basically depend on network quality. And normally we use that when the cost and code size and processing power are very limited. Now let's focus on one of the most critical section in IEEE 1344, which is a performance metric. This is where synchronization become a matter of proof, not just an assumption. Okay. These metrics basically make sure that you don't just have the time, you have an auditable, traceable, and verifiable time. Okay, what are these metrics? Let's go over them. One is offset. We already talked about the definition is instantaneous difference between the local time and the reference clock. What is the significance of this parameter? It's measure the absolute error. Next parameter is the skew, which is the offset between two peer clocks. It's not hierarchy, it's peer clocks in the same level. And it's normally used, the significance is used for pairwise alignment verification. Okay. Jitter is another parameter that we have to like audit to make sure the synchronization is validated and verifiable. Okay, and it's short-term variability in offset measurement, which impacts basically the control stability or filter tuning. Now, the accuracy is the deviation, the next term, the deviation from UTC or defined time reference. Okay, which is basically a legal and regulatory benchmarks. The accuracy is quite understandable because we cannot have a zero error in any system. It's a physical system. So the accuracy defines how we are deviated from our central time unit. Okay. Now, in our central time unit. Stability is basically defined as a consistency of timekeeping over a long duration. So this is one of the parameters that we have to audit to make sure that our time synchronization is uh, 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 passing the criterias, and it characterized by Allen deviation. Drift, we already talked about that, is a rate of the clock divergence from the reference over time. And it normally impacts the holdover design. So you have to pay attention to the drift when you want to like design the holdover state or strategies in your system. That Allen deviation that we talked about in stability, okay, is actually a statistical measure of an oscillator frequency stability. So it evaluates the oscillator noise performance. That oscillator is the technology that basically create time, create the periods of time. So when you talk about the second, the oscillation, it's the duration of one oscillation. Uh, the max time interval error is the worst case timing error in a window, and the time deviation is the RMS deviation used for network grade. These are the parameters that we use for evaluating the synchronization quality. Now, IEEE 1344 basically supports several ways to monitor performance. Okay, it could be real time or like an oscilloscope or TIA measurement. Okay, which captures rise times, offset drifts, and jitter bands, and it's used normally during the commissioning or a forensic analysis. We had an embedded logging, kind of like monitoring in Grandmaster or boundary clock, which logs the synchronization states, offset, drift, and the quality classes. And it must include timestamp of last sync and current status. These type of monitoring must be cryptographically signed for a compliance environment. Now, next one is a software-based estimation. For like NTP or SNTP, we analyze delay or offset and round trip states, and is used normally in diagnostic and drift compensation. The time quality tags, this is another monitoring techniques. In that technique, every packet or log entry includes time plus class label. So clients can track their own synchronization state. Now, we talk about a variety of topics in uh, time synchronization. Now let's talk about the synchronization budget. The synchronization budget in IEEE 1344 basically is referred to a structure quantitative accounting of all potential source of timing error. It's like electrical power budget or thermal design budget. Okay, and it provides a framework to understand and bound all timing uncertainties. Uh, the synchronization budget basically begins with the reference class accuracy, typically provided by the as a source. This reference basically shows us the baseline notion of true time in a system. Although these sources provides timing accuracy better than 100 nanoseconds, some of them is very kind of like accurate under ideal condition. In practice, the delays or antenna misplacement or spoofing attack can degrade this accuracy. Okay, therefore, the raw precision of the clock is only the starting point. So we have to include its real world behavior too. Now, on the next step, the system must consider jitter and holdover behavior for the local oscillator. We know that a jitter introduces a short time variability into the timing signals, On the other hand, the holdover reflects how well a local clock maintains accuracy during that outage of the reference clock. Okay, so this drift that we're talking about must be estimated and included in the synchronization error margin. This is very important, especially for the system where continuous access to that reference clock is not guaranteed. Okay, the network delay is another major kind of like component. Any distribution, any system of distribution time that works over like Ethernet or fiber or wireless must consider for a network delay. Fixed delay normally comes from the cable length or uh, router switching time, but there is a variable delays that comes from the traffic congestion or dynamic routing. Okay, so these delays are asymmetric and time dependent, which make them particularly difficult to model and correct unless using hardware time stepping and precision protocols like IEEE 1588 PTP. Okay, if not corrected, this delay would cause time offsets between all the nodes, and the result is a growing nonlinearity. Another aspect is when sending and receiving timing packets, the forward and reverse paths might not be symmetrical. Okay, it's a transmission asymmetry. This can be to the different cable type or switch architecture. And if this asymmetry is not measured or compensated, it could create a bias in the estimated time offset. Another aspect involves hardware time stepping capabilities. If the physical network interface card or measurement do not support precise hardware level time stepping or software level delay, that software level delays can introduce errors like in a microsecond range into the system. In high performance system like synchrophaser networks or telecom base station, this alone can basically determine whether the system meets a certain class of synchronization accuracy or not. There are a servo convergence aspect that describes how well the synchronization loop tracks the reference time over a specific time period. When we have a poorly tuned loops, it can oscillate or converge slowly, leading to a kind of like a transient error after a disturbance. Because of that, the design of the control algorithm, the time constant, the damping ratio, and the interaction with the network jitter, all of them are contribute to this component of the budget. So based on the discussion of this slide, we know that a synchronization budget basically aggregate all these components, okay, into a signal cumulative estimate of a total timer. And we have to consider that time error when we talk about the synchronization. Now, why we kind of like care about that time error that we discussed in the previous slide is because we wanted to like have a classification over the quality of our time. But why the quality classification matters? Okay, it doesn't matter if it's a smart power grid or a high frequency kind of like platform, trading platform, or a mobile network. Okay, the accuracy of time synchronization is not a luxury; it's a requirement. Okay, not all subsystems can maintain perfect synchronization at all time. You have to note that. So it's critical for each data point or control action or measurement to carry with a quantifiable statement of how confident it is about the timing. So IEEE 1344 basically mandates metadata tagging, okay, where every time tagged event must explicitly declare the quality of the synchronization. Now, we have four primary classes for the time quality. Uh, these are not just conceptual groupings. They are quantitative categories that defines uh, the hard upper bounds on time uncertainty. Okay, so we have class 0, which is the errors up to 10 nanoseconds. This is at the highest precision level. Okay, systems that operating in this class typically use atomic clock or high performance GPS. It is required in telecom timing transport layer and synchrophaser system, where kind of like the angle error must stay under like 0.01 degree. It's also essential in quantum synchronization, radar, or military missile coordination. So this is the highest precision that we could have class 0. Now class 1 is when we have the precision up to 100 nanosecond error. This class is appropriate for system that using the GNSS or disciplined crystal oscillators. Okay, and it's typically used for 5G base station or a SCADA system. Okay, and data in this class is still considered a high integrity and is reliable for control and protection. Now in class 2, we have the error up to 1 microsecond, which is acceptable for lower cost GPS receivers or a good PTP implementation, and is normally used for like the base digital substation, industrial automation, or time tag sensor fusion in robotics. But it is also good for most forensic and log integration, where millisecond resolution isn't tight enough, but nanosecond is overkill. You know, class 3 is when we have the error under up to 10 microseconds. This is an entry level synchronization quality. So every synchronization system should pass class 3. Now, if it passed class 2 or 1 or 0, it has a more precise, it has a better kind of like performance, but class 3 is the bare minimum. So it's normally used for SMTP based system or like a legacy network when it's not critical, like monitoring application is not critical. Is not acceptable for closed loop control or phase dependent calculations, but might be sufficient for data like a archival or low rate telemetry or kind of like delayed alarms. Now, every timestamp entity, it doesn't matter if it's a sensor reading or control packet or log entry or event signal, should carry a time quality tag. This tag is either embedded in the communication protocol, okay, or attached as a structured metadata in the software logging systems. accept or reject the data based on required accuracy is another aspect of how these classes are important. Like only class 1 and above are accepted for fast frequency response. So if you receive, like we have a very a kind of like high sensitive kind of system that needs class 1 accuracy, class 1 quality of time. If it get a data that is tagged for class 2, it would reject it. It should reject it actually. Okay. So having an explicit time quality classification actually make us sure traceability and legal accountability. Okay. Now, uh, at the heart of, like in the base of a secure synchronization, we have a recognition that the time is a trusted coordinate. If the time is tampered with or delayed or spoofed, the entire system can be manipulated or rendered unstable. There is several kind of like aspect which IEEE 1344 originally basically designed for that precise synchronization, and they're especially in synergy with the standards like IEEE 1588 PTP or NTP. Now, the fault tolerance in the synchronization architecture is basically is about how accurate or secure your primary synchronization sources. Now, when the failures will happen, okay, or we have an oscillator aging or corrupted time server. Now, this standard emphasizes the resilient synchronization infrastructure, okay, when the cross verification becomes a structural component for the system. The most powerful method for resilience is like multi-source validation, which rely on instead of relying on a single GPS or a master clock, the fault-tolerant system accepts input from multiple independent time sources and cross-verifies them. Okay. If one source drifts beyond an allowed tolerance window, it's rejected or demoted. This standard IEEE 1344 also recommends architectures where a secondary clock is always standing by. If the primary master fails, then the secondary one kicks in automatically. Now, detection of the failure is only one half of the story. Is a robust time system must respond safely to the synchronization loss and recover when normal operation resume. So we have fault detection mechanism like monitoring oscillator stability, watching for deviation in round trip delay, verifying synchronization message rate, and checking for the heartbeat failure, or observing jitter patterns and threshold crossing. When a fault is detected, basically we are mandated for the generation of a real-time alarm. These alarms must be designed to trigger operational modes. Okay? like control loop isolation or degraded mode operation or even system shutdown if the safety is critical. If the system loses the master synchronization source, it must enter holdover. We already talked about that. In this mode, internal oscillators are used to free run the clock. The performance of this holdover actually depends on the oscillator quality, temperature stability, or recent discipline history. Now, once synchronization is re-established, the system performs either a slew, which is a gradual correction, or a step, which is an instant adjustment, to bring the clock back in alignment. This recovery must be logged, timestamped, and verified to prevent like post-failure ambiguity. Beside that, the transition must be smooth. Okay, so abrupt corrections may cause data misalignment or missed triggers or control instability, so we have to avoid those. Now, let's talk about some of the application of this synchronization in like, for example, power system domain. Now, we know that the power system becoming dynamic and decentralized uh, in current day, and the real-time decision being made based on the measurement from distributed devices. Now, the accuracy and the usefulness of these measurements depends on the temporal correlation. Okay, if we don't have the common understanding of now, okay, measurement from different nodes or bosses cannot be aligned. Okay, so IEEE 1344 basically gave us an underlying synchronization infrastructure that makes sure the temporal integrity across the whole power grid. Let's examine like three core applications. Like one is Synchrophasor, which uses the IEEE C37 part 118. Uh, the PMUs, the phasor measurement units, measure the magnitude and the phase angle of the voltage or current, okay, in a certain instant. And they are usually working at a 30 to 120 samples per second. Okay, these measurements are time tagged, okay, and then transmitted to the central location. It could be a control center or like a phasor data concentrator. Okay, the standards that we have define synchrophasor performance in that IEEE 37 part 118, and that explicitly requires a synchronization error to be less than 1 microsecond. Why that? Because 1 microsecond error translates to the 0.022 degree of phase error at 60 hertz actually. Now, IEEE 3044 basically makes sure and enables this technology to, first of all, distributing sub-microsecond accurate time for all the PMUs, maintaining the logs and quality tags to trace the timestamp, and supporting fault detection in synchronization. When a PMU drift and is out of sync, the angle measurement become useless and it misleads actually. So it could lead to a false event detection or missed alarm. Another aspect is the sample like IEEE 61, IEC 61850 sample value and digital substations. Okay, in such a system, traditional analog CT or PT, current transformer or potential transformer signals are replaced by a sampled values. They are digitized, time tagged, and transmitted over the Ethernet-based process bus. So the merging unit that performed the digitization must sample and transmit waveform at exactly the same time within tens or hundreds of nanoseconds. That makes the protection relays receive coherent signal, okay, and the digital differential protection operates correctly, or inner device communication become consistent. Now, IEEE 1344 basically provide the precise shared time base so all the device could use as a reference. It defines how you have to tag samples and how to ensure the traceability of the synchronization and how to detect if you lost the synchronization. Without this definition in the IEEE on these criteria in IEEE 1344, basically the time coordination, sample values would be temporally misaligned, which basically means false trips, missed faults, or relay malfunction. Another aspect in the power system is the SCADA system. When we have a control system in SCADA, which is a supervisory control and data acquisition, that SCADA manage the grid operation by collecting the data throughout the system, okay, and make a decision for the suitable action for those measured data. Each of those data point could be like a voltage level or like a breaker status or a tap changer position. They all should be time tagged so we could have an accurate interpretation. Okay, all the event records and sequence of event logs should be uh, available for post disturbance or forensic analysis. The IEEE 1344 in that regard basically guarantees that the events from different stations can be sequenced without any ambiguity. And also the time correlation of alarms and control actions can be validated when you follow the IEEE 1344 for the SCADA system data. And we could basically reliably replay the system states and run run the analysis on the event that already happened, and we have it in our log history. Now there are application in also the telecommunication and aerospace. Okay, so we know that the modern telecommunication system, particularly cellular networks, okay, rely strictly on timing alignment. Okay, so it's not a legacy circuit switch. Okay, it's highly distributed, dynamically reconfigurable, and operates over a shared time slot and a shared frequency band and in spatial beams. When we wanted to like have a seamless service, all these components must share a common notion of time, and they have to be synchronized, okay, to a microsecond or even nanosecond precision. Now, one is the mobile network. One example is the mobile network synchronization. In a 4G LTE or in a 5G new radio, okay, tight synchronization is mandatory, is absolute mandation. Frame alignment across neighboring E node or G node is important. Time division, duplexing, scheduling is another important fact that requires the tight synchronization. So IEEE 1344 IEEE 34 basically uh, contributes to this by making a sub-microsecond synchronization across cell sites using like PTP telecom profiles or time quality. It defines how the synchronization would happen. So in practical term, let's say if we have a two 5G base stations and they have like a differing time by more than 130 nanosecond, the handover failure or internal cell interface can be possible and can happen. We have a degrading quality of the service, or even we could have a dropped connection. So this standard IEEE 3044 prevent this by constantly validating time alignment, okay, and enforcing the redundancy and logging every significant synchronization event. Now we have a flight data record system in aerospace, okay, that also is heavily required a good synchronization time. In that part, which is very critical for navigation and control and post-flight analysis, okay, IEEE 1344 basically makes sure that the time tags across subsystems are precise and consistent. So if we have a post-incident reconstruction, we could forensically validate that. All the telemetry between the aircraft and the ground is phased aligned. This is very important for the accuracy and the safety of that mission. Now, we have also a launch and range safety systems. Okay, when we have like a satellite launch. Okay, we have to, in this kind of case, we have to accurately track projectile motion. We have to coordinate safety abort system. Merging sensor data from multiple observation platforms is another requirement that these kind of systems have. Now, this is when IEEE 1344 kicks in and makes sure that all the instruments are synchronized to a common UTC aligned master. If there is a clock drift or a failure, they are detected in real time. Or if we lose synchronization, okay, it is compensated by holdover and logging system. Same concept goes through the autonomous navigation. When all sensors are synchronized in time, they have to be synchronized in time, and the data fusion algorithms operate on a temporally aligned input. So these standards actually provide the synchronization, okay, by defining how time tags should be applied to those sensor data and basically mandate the traceability between the local clocks. Also, it defines the monitoring and recovering from timing degradation and misalignment. So without accurate time, the sensor fusion become noisy, control decision become inconsistent, and the navigation becomes unreliable. Now, what is the best practice for time-aware system design? In traditional system, the timing normally kind of like treated as a passive background or sometimes assumed to work unless it fails. But IEEE 3044 challenges that view. This means that in your system, block diagrams, you must explicitly define the master clock, all the slave clocks, boundary clocks, time transport medium, it could be fiber into the Ethernet, and redundancy paths. So if you have like a backup GPS, it's beyond just defining the components. The timing subsystem must be designed with a failover modes or security policies or error detection mechanism. Now we have a quantified timing requirement. Okay, for example, we limit we quantify the maximum allowable time error, or and we say, like, for example, it should be 1 microsecond, or we define a quantified measure, like for example, a clock skew between nodes, which we could define it like, for example, it should not be exceeding 250 nanosecond, or time to convergence after power up, or holdover drift, okay, and should not exceed a certain threshold. These metrics are basically your design constraint. So when you design a system, and you have to consider that time tagging and synchronization with the master clock, all these parameters, all these criteria defines how well you did your design, and how well and how reliable this system works. After that, for best practices, we have to choose the right protocol and hardware. So it's not the time synchronization is not just one size fits all solution. If we choose wrong protocol, which is too complex or too weak, or over design or under design in our infrastructure, that could basically make either wasted resources or catastrophic failure. How to appropriately select that? Like, we use PTP when you need nanosecond accuracy and can afford time step capable hardware. We use NTP when a millisecond resolution is good enough, and the security feature are more important than a precision. We use RIIG for legacy system where a serial time code is needed with minimal setup. Or we use 1 PPS in a hybrid system with low processing power. Another aspect of best practice is monitor, alarm, and log everything. So this standard IEEE 1344 treats time synchronization like a live service, is not static. That means that we must implement a continuous observation, okay, and everything should be logged and traceable, like current sync status, offset from master, jitter or drift, alarm threshold. Okay, so these are all should be logged. Now, this log must be digitally signed and retained for at least a minimum time that regulators in each field would require. Like we had the example in previous slide that in finance it's 7 years. Alarms also should not only be generated for synchronization losses, but also for slow degrading behavior, like rising jitter. If we have rising jitter, we should have an alarm. If we have a slow servo convergence, we have to have an alarm. If we have a backup source drift, we have to have an alarm. So all of them should be recorded. So this is how we make sure that we are actually following the best practice for time-aware system design. Now, this is our discussion. If you have any question, please let me know. And thank you for your attention.